Welcome to this Intro to Machine Learning course from Rolla Dolly. Rolla is an AI engineer and has a PhD in neuroscience. The course starts with the fundamentals, covering what machine learning is, how it differs from traditional approaches, and when it's used. It then dives deeper into the mechanics, exploring different models, algorithms, and training processes. Next, it covers generative AI, before wrapping up with the architecture of AI systems and how to design and deploy them effectively.
Hello, everyone. My name is Rola Dadi. I am a machine learning architect. And what I want to do here today is to give you some background information on machine learning. So this is really a primer for people without ML knowledge. It's not supposed to go into great technical detail. I just want to give you practically the lay of the land. And so I'll take you through this. So just a little bit about myself. Again, I'm a machine learning architect at Rapid Scale. We serve the US market, and I help customers build machine learning systems every day. I come from an academic background, so I have a PhD in neuroscience and bioinformatics. I graduated from McGill University in 2017. I like to say that I was interested in human intelligence, and now I work more in artificial intelligence. I really like to compare and contrast the two occasionally. I'm also an AWS enthusiast, so I'm an AWS community builder. I'm the AWS Montreal co-lead, and I'm also an AWS ambassador for Rapid Scale. I'm a gold jacket ambassador, which means that I have completed all 12 certifications. On a personal side, I am a mother of two little angels that keep me busy, and I love to cake, although I don't get to do that as much anymore. So in terms of what I've got here today, it's a series, a 4-part series. I'm going to go through what I'm calling ML 101, which is an introduction to machine learning. ML 102, which is really ML under the hood. So we'll talk a little bit about algorithms just to peel a layer off and give you a better understanding of what is going on. ML 103 is an introduction to generative AI, and 104 is about architecting a Gen AI system. Okay, so they shouldn't be long. I'm expecting about 30 minutes a lecture, hopefully. I do tend to go off rails sometimes, so let's say 45 minutes, and hopefully it's useful. So I'll see you in the next one. Hello again. So let's start with ML 101. So this is an introduction to machine learning. Again, it assumes no knowledge, and this is supposed to be for a beginner audience. So I'll go through what machine learning is in terms of definition, how it's different from computer science, how it's different from statistics, where to use it and where not to use it, and a little bit about the machine learning life cycle. Talk a little bit about ML on AWS. It's fairly similar to how it works on cloud in general, but I am an AWS heavy practitioner, so I'll choose AWS, and then I'll look at artificial intelligence versus human intelligence, again, in ode to my doctorate studies. Okay, so what is machine learning? So in terms of definition, and if you ask Google, then you'll get a definition from Oxford Languages, which says machine learning is the use and development of computer systems that are able to learn and adapt without following explicit instructions. And by using algorithms and statistical models to analyze and draw inferences from patterns in the data. I don't know if you understood anything from that, but it's pretty long. So let's deconstruct this a little bit. So machine learning systems are computer systems. They are based on algorithms and statistical models, and they learn patterns in the data without following explicit instructions. So these are the 4 core things I think in here. And so if I were to rewrite this, I would say that machine learning is really powerful mathematics powered by computer systems that learn patterns in the data without explicitly being taught. That's my definition. And that's exactly what it is. So it's math, it's computers, it's data. And so how is it different from computer software? So ML has been called software 2.0. So how is it really different from traditional software? Well, there's two steps to any software system. There's the development step and then there's the deployment step, right? So in traditional software, during development, you've got yourself a computer, and what you do is you sit down and you write your code. This is the formula. You sit down and whatever language you choose, you write a set of statements, right? If this happens, do that. When this happens, do this other thing, and so on. So that's your code. And then what happens is you give the code an input. The computer crunches all of this and gives you an output, right? Now, how is that different in machine learning? Well, in machine learning development, this is what we call training. And you've got a computer, but then instead of actually writing the formula, what you do is you give it the input and you give it the output. This is a specific type called supervised learning, but it's one of the more popular types, so that's what I'm going to use. And so you've got yourself a computer, you give it the input and you give it the output. It crunches the information and it tells you the formula. So this is really interesting in places where we don't know the formula ourselves. We don't think there's complexity, or there's things that we just don't understand, right? So this is how it works. That's the main difference, is that in a traditional computer system, you write the formula, and in a machine learning system, the formula is the actual output during training. The formula, there's a lot of other terminology. The formula is a pattern, it's an algorithm, it's a recipe. Instructions in machine learning, it's the actual model. The term is the model. Now, when it comes to deployment, what ends up happening is you deploy this software system on a computer. Your user puts the input in and gets an output. Now, in machine learning deployment, this is what we call inference or prediction. Again, you deploy this formula now that you got out of training, you deploy that and you get an output. So at deployment time, software and machine learning systems look fairly similar, but the difference mainly is at training time. So how is it different from statistics? There's a lot of people tend to confuse statistics and ML sometimes. So let me tell you a little bit about the different types of analytics. We distinguish 4 types of analytics. So there's descriptive analytics, which explains what happened. There's diagnostic analytics, which explains why it actually happened. There's predictive analytics, which forecasts what might happen in the future, and prescriptive analytics, which recommends action based on that predicted forecast. And as you move through this to the right, there's more insight and foresight. And so statistics really is at a different scale than machine learning is. Machine learning really excels at prediction and foresight. And so both statistics and machine learning are both part of the dataset toolkit. They both aim at defining mathematical representations of the real world, which we call a model. And but statistics is more concerned with understanding population descriptions. What is your mean? What is your variance? What is your sample size? How does the sample represent the bigger population? Things like that. Whereas ML is more concerned with predicting unseen data. So more projecting based on the information I have today. Can I project later? And so the machine learning superpower is really prediction. It's using information you have to predict information you do not have. And the importance of that is really reducing uncertainty and being more prepared. And so as humans, I think we have always had a fascination with prediction. So I took Greek mythology in my undergrad, and this is the Oracle of Delphi, which was one of the most famous Greek oracles, and people would go in for predictions. And there's a lot of stories of war in the ancient world that were based on different predictions. And I mean, fortune tellers are forms of predictors, although they're a different backend than ML, but there is a fascination, there's a human fascination with prediction. And so I'll take you through some ML terminology. Artificial intelligence, or AI, in the field is defined as techniques that enable computers to mimic human behavior. So these are things like robots. These are things that just allow systems to behave human-like, right? So what is machine learning or ML? These are AI techniques that allow computers to learn without explicit programming. So these are specifically mimicking the learning capability of humans. And so you've got artificial intelligence, which is the bigger bucket, and machine learning is a subset of that. So what is artificial intelligence that is not machine learning? Well, there's things like robotics, because robots mimic human motion and other aspects, but they are code-based, or they're programmed specifically to do that. There's NLP, syntax and semantics. So NLP can be, if it's based on learning, then it could be part of machine learning, but there's a whole part of NLP that is really rule-based, that is outside of machine learning. Deep learning is a subset of machine learning, which uses multi-layer neural networks inspired by the human brain. And so again, that's a subset of ML. Other algorithms that are not in this are, for example, SVMs, logistic regression, linear regression, XGBoost. There's a whole lot of different types of algorithms, and we'll go through that in the second lecture. Generative AI is a type of AI that allows computers to generate new content, and we'll see again across the series what that really means. So the rise of ML, I find this really interesting, and I wanted to mention it. So the AI is a field that has been around for a really long time. These are the AI godfathers, what are known as the AI godfathers. There's Geoffrey Hinton, Jan LeCun, and Joshua Bengio, and they did their PhDs in the 70s and 80s and 90s on machine learning. They have done a lot of work on the deep learning and a lot of really cool techniques. They've really revived the field. That's why they're called the AI godfathers. But the first academic papers on machine learning are as old as 1940s, right? And so why did it take so long? Why has it been 80 years? That right now is super popular. And there's a number of reasons. So there's an increase in number of devices in data, in just information. There's an increase in computer speed and memory. So now we have data, we can process that data. And there's an explosion of algorithms and mathematical models. And there's increased demand for customized solutions and data-driven systems. I think there's a realization of the potential power in data and ML. And so if we look at this, the ML foundational pillars, based on the definition I told you, so machine learning systems are really based on data, mathematical algorithms, and computer systems. And there has been a huge conversion and an explosion of information across all these fields. And one of my one of the resources I really like is this McKinsey diagram. Let me show it to you. It's really cool. So if you look at why AI, and then they show you some of the things that happen in the explosion of data. So the opening of the internet in 1991 has really just exploded the amount of data that we have. We're being tracked across everything we do. And so you can see here across all of the things that have happened, and it's really interesting to see that. And I've played with this several times. There's algorithmic advancements. Again, you can see all of the things that, some of the really major things that have changed the field. And then you've got increases in power, and they all converge to here to 2009 with Andrew Ng using GPUs to train deep learning models and so on. And you can look at this. This is one of, I really like this resource. And so, yeah, we're at an era where computers cheap. There's a lot of smart people creating a lot of really cool algorithms, and there's a lot of data. So it's really great for machine learning. Okay, so when is ML a fit for your use case, and what are some anti-patterns? Anytime there is data, machine learning is a possible option, right? Because it can learn patterns in the data. It is a great fit, though. I tell my clients it's an actually great fit, a no-brainer when there's scale. So because machines scale much, much better than humans. So if you have an operation, you're running a company, and you want to double your operations, if you have a system that is not based on machine learning, for example, you would have to hire double the people, by double the desk, by double the resources, the space, train, and so on. Whereas if this was a machine learning system, let's say in the cloud, then with a few clicks, you could potentially double or triple or so on. You could scale really well, really fast. So when there's scale, machine learning is a great option. When there's change, because we're now living in a global world, it's an interconnected world, and things change very fast. And for us to detect change and then try to understand it, try to model it, try to make predictions out of it manually, or it's going to be things move so fast that we can't do that cycle efficiently. But if we have an MLOps system, then it can detect a change and trigger training and deployment and so on. So again, with change, ML and MLOps are a better solution than other options. And in terms of complexity, because when patterns are too complex to tease out, machine learning shines in complexity. And so when is it a great fit? Scale, change, and complexity. When is it an anti-pattern? Well, I used to say when you don't have enough data or bad quality data, that is, of course, making the assumption that you want to train your own models. Today, there's a lot of pre-trained models, so you don't have to do that. So if you do want to train your own model, then data is definitely a prerequisite, but you can use pre-trained models. If simpler solutions exist and do the trick really well, then you don't really need machine learning. There is an onboarding cost, right? There is a skill set required, there is a setup required, and so on. So if your systems work and they're fine, maybe you don't need it. And if it's not a cost effective, right? If you're using a system, it should be cost effective. And there's a word of caution I wanted to say. In the previous decade, there was a lot of disappointment in machine learning because I think there was a huge disconnect between the engineers on the ground that were optimizing for technical objectives and the business itself, which was looking at their business goals. And so there's a disconnect between the actual technical objectives and the business needs, because the engineers would optimize the objective function, the model would work, but it wouldn't be tied to the business, and that created a bit of frustration. And so if you are an ML engineer, ML serves the business. So you need to connect, you need to model your problem to serve the business. And we'll talk a little bit more about that in the life cycle. So this is about the automation life cycle. So machine learning, machine-human interaction skills. People assume that people are sometimes scared about ML. It doesn't have to be an all or none situation. There's different configurations that you can set up in your company. So on one scale, you've got the human-only system. So these are systems run fully by humans. On the very other end of the scale, you've got systems that are fully run by machines, right? So there's full automation. And there's very, very few systems, I think, in the world that do this, very few companies that do this. It's certainly not everybody, although we try to set these systems up, but again, you don't have to. In the middle, there's a whole spectrum of things. So there's shadow mode, where the machine learning shadows the human, but its output is not used. This could be done for compliance. This could be done for training. This can be done for different reasons, for understanding systems. Then you've got AI assistance, where the human is the primary driver, and then there's a machine learning system that the human can tap into as required. So these are people in call centers, for example, have an auxiliary system that helps them do their job fast. And there are different positions where we put an auxiliary system that helps the person, but you're still interacting with a human first. And then we've got partial automation where the machine learning does the actual work. It is in the forefront, but then there's human gating and validation and approval. So there's some sort of control by humans. And ML is an iterative and experimental process towards maturity. So you start early and you keep iterating towards the system that you are comfortable with. And I always tell clients that, if you wait for technology to prove its worth for the rest of the industry before you jump in, then you might be playing catch up for a really long time, right? So stay up to date with new technology, try to dabble into it, and just to at least be aware of what's going on in the field. Okay, so the machine learning life cycle. This is my 5-petal flower that I've illustrated. So always we start with the business. Again, tech serves the business. We start from business needs. We identify the goals. We frame the problem. We choose the metrics and plan the process. We come into the data. So we collect, we explore, we transform. Then we go into the model domain, we choose our model, we train it, we evaluate it, we optimize it, and then we deploy it, and then we maintain it and monitor it, and so on. So some interesting steps there. So the most important one, I think, is really defining and framing the problem. And so what this means is that, again, the business has a goal, a business goal, and there's a million ways that that business goal can be transposed into mathematical space, right? What is the proxy? What metrics proxy that business goal? What does it mean in mathematical representation? So that's called framing the problem. And that's probably one of the most important steps, I would say, when you're an ML engineer, is to really understand the business goal and formulate it in mathematical terms. Then there's the data preparation phase, the model phase, the deployment, and the operations. So I'm a great fan of AWS, but again, this works pretty similarly in most clouds. What I want to show you is that these clouds, they provide services to different personas. This is a fairly old representation. So a lot of the services, they have a lot more services now, but I just want to show you the layering. And so at the bottom, at the bottom here, we've got frameworks. These are chips. These are base libraries that people can use. So these are systems that an ML engineer would use to build from scratch, but not everybody would need that. Above that, they have a layer, which is a little bit more abstracted. So this is SageMaker, for example, has a lot of abstracted capabilities for you. This is, for example, where a data scientist might thrive. Above that, they have a layer of pre-trained models, so ML as a service. And this is for everybody. It's an API call that you can make, and these are models that provide the AWS, for example, maintains. And so as you go up the scale, there's an abstraction, so there's ease of use, but then as you go down, there's a lot more control. And so if you're interested in machine learning, wherever you are in that spectrum, there is a tool for you. And so you just need to identify where you are here and look there. This is true for generative AI as well. It's the same stack. So at the bottom, you've got your infrastructure. On the top, you've got your platforms. And then on the very top, you've got your SaaS models. And this is my last slide. So this is the brains versus bots. This is an article that I had wrote previously about comparing humans and artificial intelligence. So they're both predictive machines, right? So I told you through this presentation that machine learning is the main power is predictive power. it's interesting that brains are also predictive. I think that caught neuroscientists by surprise. Um, there's a lot of evidence today that the brain predicts actions before they happen. So when you drink water, for example, you get satiated before the water hits your stomach, right? Or travels through your system. And that's a prediction from your brain that your system is going to go through homeostasis, right? So there's a predictive capability. And that makes sense, right? And there's a lot of examples about this. And it makes sense because an ancestor who would have waited to react would have been eaten and not survived. And so it's interesting. I when I learned this, it was I was a little surprised, I must say, but there's a lot of evidence today to support this. In terms of counts or size, of course, brains, the main processing unit of the brain is the neuron. We can look at synapses, which are the neuron to neuron connection. And there's about 100 trillion synapses in the brain. The equivalent to that in the bots are parameters or weights. And today there's about 2 trillion in the state of the art models, roughly about 1.8, but I'm averaging to roughly 2 trillions. And so brains are still about 50 times more interconnected than any of our models. And the brain is still a lot better at integrating data holistically. We have been evolving for about 300,000 years. And so we handle information still a lot better than models do. So in terms of winner, the brain is the winner here. In terms of training time, again, the brain has been evolving for 300,000 years. And your own, well, there's a typo here, but your own instance has been fine-tuning for the length of your own age, right? Bots, however, are a lot younger. So I just told you the field is about 80 years old and started in 1940s. So let's say about 100. But it is a product of human ingenuity, right? There's a lot of effort that is being dumped into artificial intelligence. There's a lot of money going there. There's a lot of interest. And so, so the bots have had a lot less time in terms of training time. Machines have a way to go still to catch up with the brain. So the brain wins, but not, I assume, in another few decades, this would not be the case. Speed, again, brains depend on neurotransmitters diffusing through liquids. So these are the neurotransmitters that are used to communicate. And that's estimated at about, let's say, 200 hertz. Bots depend on electrons running through transistors. And today, CPU clock rate is over 10 gigahertz, right? So bots are about 50 times faster than brains are or could ever be. In terms of input modalities, we are tethered to biology. Our brain gets input through our 5 senses, whereas bots have unlimited input streams. So if you've ever built an Arduino or you know, any particular system, you can buy tons and tons of different IoT devices and input devices that you can add through the systems, and you can figure out how to process that data. So bots have unlimited input streams, which we cannot match. And so machine learning systems have huge potential because of their speed and augmentation capability. So the fact that we are tethered to biology kind of gives us the short end of the stick here. So it is no surprise that AI will be the workhorse of the future. So I suggest everybody learns ML. And these are some of the resources that I've used along my way getting into the field. I've been in the field since 2012. So I put them here. I'm releasing these notes as well, so you could be able to click through these. And that's it. So this is ML 102. So this is machine learning under the hood. So what we're going to do is we're going to delve a little bit further into models and so on. Again, not too deep or not too technical, but a lot of people say, well, what's happening a little deeper? And so I'm going to take you one level down. And so I'm going to start with the types of machine learning. So there's different types or categories of machine learning. And right now, the major classification is 4 different types. So there's supervised learning. This is when the model learns from data with labels. So we already know what the right solution is, and the model tends to mimic that. Unsupervised learning is when the model learns from data without labels. So we do not know what the right answer is, and then the model tries to make some sense or some pattern in the data. Reinforcement learning is a type of machine learning which solves multi-step problems by maximizing a reward function. And generative AI are models that generate new content. And if you read a machine learning book before November 2022, you wouldn't have seen the 4th type. So before November 2022, most books would have told you there's 3 types of machine learning: supervised, unsupervised, and reinforcement learning. In November 2022, OpenAI released ChatGPT to the public, and of course, it caught fire. And since then, I think everything we can hear of is Gen AI. So again, if you're reading older resources, you would not see that. Now, what the terminology that I'm going to use for the 3 classes of ML that are not Gen AI is predictive ML or classical ML. Some people call it traditional ML, or and then Gen AI. So I'm going to call them predictive ML and Gen AI. And you have to remember that AI or ML is really a set of tools. It's a toolkit that solves problems. It's a general purpose technology. Andrew Ng always says it's electricity, right? It's the new age electricity. And it is what it is really is mapping input to output. And the last decade was a lot about optimizing supervised learning. So if you've been in the field for a really long time, like I have, it was really a lot about supervised learning. We had a deep learning boom a decade ago, and now it's all about Gen AI. So the prediction is that this decade is more about Gen AI. And one interesting thing that I wanted to mention is that if a model is small, and we'll see what that means. What does it mean for a model that is small? But let's say if a model is small, what increasing amount of the data will eventually plateau performance, because we say the model overfits, which means it memorizes the data. What we're saying, and this was true for supervised learning, that was something we really watched out for. That is not true for generative AI. We're not seeing overfitting for generative AI yet. And so the more data we give it, the better performance. So there's a huge difference in performance between supervised learning and generative AI, in that we are not seeing overfitting yet. And that's partly because these models are huge. And so the amount of data that it would take them to overfit is probably quite huge, but we're not there yet. Okay, so let's take a step back. What is a model? And so again, like I told you before, a model is a mathematical representation of a real world system, right? It's a model, it's an algorithm, it's a formula, it's a pattern. Mathematically, it's an equation. And the way I think of them is machine learning models are really big statistical calculators, right? It is just playing with numbers and tuning them the right way. Model components, these are what we mathematically represent things. Again, we're not going to go into too much technical detail, but it's just good to know some of these things. So the Y is the class to be predicted. This is what we're trying to predict. It will be the model output. What we call X is the input data. So these are also called the features. So this is the information that the model will take in to predict the model output. the parameters or the weights are tunable numbers in the model that encode the learning. So we'll see some formulas. And of course, what really matters as well is the model architecture class. So this is the actual formula or equation, and we'll see a couple. And so the model class defines a mathematical formula used. So for example, a linear regression class uses a formula in the shape of y equals ax plus b, where y is, of course, the output class. This is what we're trying to predict. X is the input features. This is what we are, what the information we have. And A and B are the parameters. So these are the weights. And what will happen, we'll see an example of this. What will happen is that the model will try to find the right values of A and B, where if given X, it can predict Y, right? And this in this way, the way I've written it here, it looks like this is a single column, and it could be. But in reality, this is a series of columns. So this would be a vector. And so it would be y equals, if I would expand it out, it would be y equals a1x1 plus a2x2 plus so on, anxn plus b. Okay. Another example, so if logistic regression, for example, this ends up, this is used when y is continuous. A logistic regression is used when y is discrete. And again, if you don't know what these are, don't worry about it. I'm just trying to show you a little bit under the hood. It's not necessary for the rest of the exercises, but just in case you are interested. So a logistic regression is you take the linear regression model and you pass it through a sigmoid function, which is an activation function. Again, if you don't know what that is, you don't really need to, but the idea is to show you that underneath these systems is an actual mathematical equation, right? And this is the simplest one. So I put these here because they are the simplest ones. But as models become too big, the exact mathematical equation becomes too complex. And so we visualize their architecture with abstract diagrams. Okay, and we'll see a couple of these. But again, at the heart of it is a mathematical equation. And so these are some of the types of algorithms. We've got linear regression, logistic regression, decision trees, random forest, naive Bayes, support vector machines, SVMs, neural nets. These blue ones are for unsupervised learning, so nearest neighbor clustering and some dimensionality reduction. Again, this is a lot of what predictive ML was concerned with, is choosing the right class of model, understanding what these models do, what is the equation underlying them, where does it excel, when do I use it, how do I optimize it. This is not so much, this is not true, of course, for Gen AI, but I just wanted to show you if we peel one layer up. So we're not going to go into these. I'm using them as an example to explain to you what parameters are and hyperparameters and so on. I do want to go a little bit into deep learning or neural nets because they are the underlying foundation for a lot of things, including Gen AI. So deep learning, the human brain is made of different layers, 6 layers to be exact, of neurons that are stacked. And the way the human brain works is that neurons interconnect with each other. And there's thousands and thousands of connections per neuron. And this is an image from Ramon Cajal, the father of neuroscience. And you can see the layer of neurons. So this is a layer and this is a layer, and how they interconnect. And so neural nets, artificial neural networks, what they try to do is mimic that behavior. And so what you've got here is a neuron. This is a processing unit. This is at its heart is a logistic regression function. And we stack them. So there's a layer here. This is the input layer. And then we've got another layer. So you think of them as you've got layers and layers and layers, and this is it. You've got layers and layers and layers. And this is the first one is called the input layer. The last one is called the output layer. And everything in between is called a hidden layer. And what these are, the connections here, but from neuron to neuron, are what the parameters are. So this is the strength of connection. The parameters, what they do is they encode the strength of connections. Again, you don't need to know that, but we're going to see. So again, I didn't put the formula here because this would be quite complex. These would be logistic regression, so these would be, and then they would connect to each of these. Each of them would connect to each of them. And when I was in graduate school, we did actually write those, and we coded them up in Python and so on, but we do not need to do that here. But you're going to see another, so these are the underlying systems, again, that encode transformers and GenAI, but we don't really need to get any deeper than that. So what is a parameter and what is a hyperparameter? So a parameter, a model parameter is a tunable variable. So this is something that the model can change, and it is internal to the model, and whose value can be learned from the data through training. Okay, and this is what encodes the learning of the model. So two different models that have seen different data would have different parameter values or different weights. Parameters and weights are the same, refer to the same thing. What are model hyperparameters? Well, these are variables that are external to the model. Their value cannot be learned from the data. But what hyperparameters do is that they control the learning process. And so examples of hyperparameters are the learning rate of certain algorithms, the number of epochs, this is how many training cycles the system went through. Regularization, this is a system that constrains the, the model from getting too big. So when you download a model, a pre-trained model, what you're actually downloading are the parameters or the weights of that model. You are not, I don't know that hyperparameters are always included. They don't affect the model performance. But so models are sized by the number of parameters, and hyperparameters are good to keep track of because they might explain, they might allow you to troubleshoot through things, but they're not, they are not important for the actual learned information. They're important for the learning process. Okay. Okay, so solving a supervised learning problem. We went through this in the previous session, so I'm just going to go through it very quickly. And so again, we start with the business. Tech serves the business, and so we always start with the business. We understand the business goal. We try to frame the problem, which means we transform that business problem into mathematical notations. We understand what metrics are great proxies. We plan the process. Then once we do that, we go into the data realm. We collect data, we clean it up, we decide on what our features are, what matters. And then we get into the model domain. So we select a model class. We decide, is this a classification? Is it a regression? What model fits best? You know, am I running a neural net? Am I running an SVM? I don't think anybody runs SVMs anymore, but they were very popular before the deep learning boom. Am I running an XGBoost, a random forest? And so you set that model, you train it, you evaluate it, you optimize it. And then once you're happy with its performance and it generalizes, it's very important that it generalizes well. Then you deploy it and you'll maintain it. Okay. And so what does training a supervised model look like? Well, what happens is that, again, it has the learning itself is encoded in these weights or parameters. What ends up happening is that the model, when you start training, it initializes them at random. So it starts them at random. It makes a prediction. So it says, okay, well, this is in supervised learning, so I know the answer. We know the answer to these instances we're looking at. And so it makes a prediction, and then it looks how far is it from the actual data. It calculates some sort of metric. It could be, we call it an error, but it could be, in reality, it's optimizing an objective function. So that could be, it could be maximizing accuracy, for example, or minimizing error. So that the general term is optimizing objective function, but I'm making the assumption here that I'm minimizing an error. And so I calculate the error between the model predictions and the real answers. And then it goes in and edits the weights to reduce that error. And then it tries again. And so what it does is it repeats the cycles 2 to 4 until the error doesn't go down. And I'll show you an example of how this is done in one of the demos. So you start the models, you predict, you calculate an error, then you adjust the models, and you keep doing this until you can no longer reduce the error. Okay. And so I have 3 demos here. I'm going to put them in separate videos. And so I'm going to demo how software is different from machine learning systems. I have a little notebook which I'll release to you for you to play with. I'll also demo this training, how that works with the linear regression, which is a very simple model. And I also want to demo the TensorFlow playground, which I like very much. So I'm going to release those as separate videos. And that's it for this one. Hello again. So this is the demo that is with the ML 101 lecture. So what I'm going to demo here is the software versus ML approach to solving problems. And then I'm going to demo the model training visualization. Okay, so let me go here. And so what this is a notebook, a Jupyter notebook that I will again release for you to play with. And what I'm showing here is how we would solve this Celsius conversion from Fahrenheit, or Fahrenheit conversion from Celsius using software versus ML. Okay, so for traditional software, we do know the formula that encodes Fahrenheit to Celsius conversion, and that's the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. So now, given that I know this, I can write a function that goes in and, given an input in Celsius, goes in and returns a Fahrenheit temperature. And so this is my formula or my code. Again, this is a single function. It's simple for demonstration purposes, but you can imagine that this is a larger piece of code. And then I am going to deploy it, which is here just asking for user input, but you can, again, imagine that this is a more complex system. And so if I am to run that, it's going to tell me, well, enter your temperature in Celsius. I'm going to enter minus 27, which is the temperature here today in Montreal. And that's going to tell me that it's minus 16.6 Fahrenheit. Okay. So again, I wrote my formula, which I already know. I wrote my rules. I know the rule. I wrote it up. You deploy it, and then you allow your users to interact with it, and then you maintain it. Now, what happens in a machine learning system? Well, in a machine learning system, what usually happens is you do not know this formula. Okay, what you have is data. And so let's say I work for a company, and that company has both Celsius thermometers and Fahrenheit thermometers in the field that are collecting data all the time. And what ends up happening is that the Fahrenheit thermometers, they break. They broke, and it's too costly to fix, and there's a shortage. So we need that data, we need that information, but I don't have a way to collect it directly. But my Celsius sensors are still picking up signal. And so what I want to do is to try to predict the temperature in Fahrenheit for my downstream systems from the sensors in Celsius. Okay. And so I'm going to download my data, and I want to show you what this looks like. So this is a set of data. This is a single file, temperature.csv, which again, you're going to have access to. There's 2 columns here. This is the data in Celsius, and this is the data in Fahrenheit. And if you go down, there's about 300 different rows in this. Okay, so this is the data that we are using. And so here, I'm going to download this data. And again, it shows what I showed you, right? There's the first column is temperature in Celsius. The second one is in Fahrenheit. I've got 300 different rows. And there's some statistical metrics here. And my min, it goes all the way from minus 43 Celsius to 120. Okay. And this is data, of course, that I generated myself with the formula plus or minus 30 degrees of noise. So you're going to see that I've added some noise into there. Okay, so if we plot this, this is what it looks like. So there's a temperature in Fahrenheit and the temperature in Celsius, and you can see that that's the little noise I've added. Now, it's easy to look at this because it's two columns. So, and I've designed it that way for the reason because it's easier to see things. In the real world, there's very few applications for this for a single column. And so there's a lot more columns and features in the real world, and visualization becomes a lot harder. But again, I'm making it two-dimensional for you to see the difference. Okay. So now I've got this information. This is my information prior to the sensors breaking down. So I do have some information. And now what I do have is my Celsius sensors are still picking up data, and I don't have any Fahrenheit anymore. And what I'm trying to do is take this information and predict my Fahrenheit for downstream systems. Okay, so how am I going to go about this? Well, I'm going to import NumPy and sklearn. Scikit-learn is a really good, it's a fundamental library in machine learning. What I'm importing here is linear regression, which is the model class. And this is for evaluation, and this is for splitting the data. We'll see in the code later. What I'm doing is I'm pulling my X, which is the Celsius column. This is my input or my feature. And I'm pulling my Y, which is the actual column that I want to predict. This is my output. And then I choose a model class. This is a linear regression because the output is continuous, but also because, I mean, I could see it's a line. But usually there's a lot of work in predictive ML in understanding what these model classes are, what is the underlying equation, what inputs do they take, what outputs, how well do they do, what space of mathematics are they really good at, and so on. So there's a lot of work in predictive ML in terms of knowing your algorithms and which one to use. That's not true for Gen AI. But okay, so for this one, I'm going to use linear regression. And so I've initiated a model that is a linear regression model. I'm taking my data, I'm splitting it 30-70, so 70 would go to training and 30 would go for testing. The reason we do this is we want the model to learn a pattern that can generalize beyond the data that the model sees. If the model does really well on the training data and does terribly on the test data, then what we say it overfit, which means it really memorized the information, which is not what we want it to do. We want the model to generalize on the test data. So we pull out here 30% of the data that the model will never see. And once it tunes its parameters on the training data, then we'll use that test data to evaluate whether it generalizes well. And here we're training. So sklearn is really nice in that you can use model.fit to predict, and then model to train, and then model.predict to predict. And so we're training here, and then we score the model by taking the R² coefficient, and then we look at some metrics. So let me do this. Okay. So this model after training, and again, we'll look at a linear regression training in the second notebook, but after training, this model did 0.96 R². These are, I'm pointing R², yeah. So this is 96 R² on the training and 95.9 on the test. The fact that these two numbers are really close tells me that it's not overfitting, that the performance on the test set is similar to that on the training set, and so the model is generalizing. Okay, so now I'm going to look at this model. I'm printing the coefficient of determination, which is the R², which we've printed out here, but also the intercept and the slope. So again, a linear regression is in the formula of y equals ax plus b. B is the intercept and a is the slope. So these are the two parameters that the model has learned, and I'm printing them out. And so when I print them out, this is what it looks like. And so when I run this, so the ML system after training thinks that the temperature in Celsius is 1.8 times the temperature in Celsius plus 32. So this is fairly close to the actual formula that we know is true. Again, this depends on how good your data is, how much noise is injected. Why didn't know it exactly? Because I injected noise and it didn't train that long. There's only 300. So the more data you have, the cleaner your data is, then the more accurate your model is. Okay. And so now that I've got this formula, I've got this formula, then I go in and deploy this model. So I'm using the model.predict to get a prediction from this model. And so let me pull that out. It's going to tell me what did you do. And I think I used minus 27. And again, this tells me based on the software system that I wrote above, it's minus 16.6 Fahrenheit. And then based on the ML prediction is 16.51, which is very, very close, right? And so this is that's how these two things work. If you know the rule, if you know the formula, you type it up. And if you don't, and you have data, then you can infer that formula from the data, okay? So again, I'm gonna release this for you to play with. Now, the other model, I want to just see if all of these are installed. This is another computer, so I just want to make sure. Okay, so what this is again is a linear regression model. What we trained in the first notebook is a linear regression model. The linear regression model equation, of course, is the y equals ax plus b or wx plus b, no matter how you want to call it. What the objective function that this model optimizes is a least square, and this is the equation. And no, this is the error that it calculates. And so it's minimizing this objective function. Anyway, that's not information you need, but anyway, this is what's happening under the hood. So I've got some functions here that train this model, and we're not going to go into it in details, but like I said in the lecture, the model initializes the weights at random. So this is the initialization code. It calculates an error. So this is the cost function it's calculating. It predicts, right? Because it has to predict, then use that prediction to calculate an error. And then it updates the parameters. So these are the three things that we've seen in that loop. And it runs gradient descent, but that's okay. And then I collect the cost history and so on. Okay, so there's some functions here that are useful. Again, I'm downloading the same file, the temperature.csv file, which we just looked at. I'm going to load it up. And then again, it's the same one. So we've got 300 going from minus 43 Celsius to 120. Okay, so these are hyperparameters. So if I go back to this model here, where is the temperature the temperature in Fahrenheit is what I want to predict. That's my Y. The temperature in Celsius is my information that's given. That's my X. That's my input data. The two numbers that I actually trained that were tuned in this model are this intercept and the slope, which is, if we go back, is really we found what this 1.8 and 32 are. So if I go back here, actually, it's this number here, the W and the B. So these are my parameters, okay, my weights. My hyperparameters are going to be here for linear regression is the learning rate, which I've set at this, and the iterations. These are the number of epochs. This is how many runs it's going to do of this cycle of calculate, predict, calculate, error, update, weights. This three system, it's going to do 10 loops of that. That's the epochs or the iterations, okay? And so now I'm running the gradient descent. So I am running this model. And then I'm going to print the history. So what I'm showing you here, this is iteration number 1. It's going to do through 10. So when it started, what we looked at this. So these are my actual data. This is my actual data that I showed you before. And this is the model prediction, okay? So it initializes the models at random. and then it makes a prediction, and this is its prediction. And so it calculates a cost, and the cost here is 4445.3, right? There's no units for this, it's just a number. But we have to, because this is an error, we have to bring it down. And so what does it do? Well, it goes into iteration 2, so it updates its weights. So now it predicts that this is a better prediction. It updates the weights, creates a cost. Now it's 2028, and then it goes again, goes through another cycle. And so now it has this guess with this cost, this guess with this cost, this guess with this cost. And by the end of it, what we've got here is the last iteration. Again, I stopped it at 10. We can go as long as we want. Again, we don't want to overfit, but now it brought down the error from 4,000 roughly to 400, and this is a better fit. This is what it thinks that this model is. And so if I plot this cost, we started at 4,000 in the first iteration, and then it brought it down and down and down and down up to, and when this flattens out, when this plateau is done, it doesn't move anymore. That's when you know that it can't learn anymore from that data, so that the learning is complete. If I plotted this and it ended up here, then I know there's more learning potentially because I haven't plateaued. Okay, so this has plateaued. It learned the whole system, and this is what the observed versus predicted values is. If I plot my actual data and the data I would get from this model, this is what this thing looks like. Okay, I have one thing to demo before I let you go. I really like this playground from TensorFlow. What this is a neural network, and you can play with this. So these are the inputs. There's two inputs. There's x1 and x2. So what are we looking at here? We're looking at, this is x1 and x2, right? And what you see is, so there's x1 and x2, and the color is the actual y. So this is a classification problem, and you're trying to classify any particular row as blue or orange. And so what you see here in the color is the actual label, or what you're trying to predict, blue or orange. And you got two features, which are x1 and x2. And what you got here is a neural net. So this is the layer, the input layer. And then you've got two hidden layers, which I can delete or add. And then you can also add the number of neurons or delete them. Okay, so I can add neurons or delete them. And you have got four different sets of information here. Okay, so this is the simplest case, is when you've got two different classes that you can separate linearly. Okay, so what is going to happen, so this is the simplest case. So even if this can be solved by a logistic regression. So I've removed all the layers. This becomes simple logistic regression. And what you see here is the features. And again, the color of the dot is the label that we want to predict, and the background is what the model thinks. And so we've succeeded when the color of the dots aligns with the color in the background. And so you can see that this, even a simple logistic regression can solve this problem by creating a line there. Right, now I wanted to show you some things here. So if I look here, these are my inputs. The color is my label or my output. And if I look here, what I have is, these are my weights, the connection strength of input. The connection strength is my weight or parameter. So this is the parameter. And then what I have here is a set of hyperparameters. This is what's controlling my learning. So this is the epochs. This is the iteration, the number of cycles it goes through. This is the learning rate. This is how fast of a jump it moves between epochs, and this can be tuned. This is the activation function. This is the a mathematical function that again is imposed on the system. And then there's regularization, which is not applied here, and regularization rate. And you can change this to regression. You'll see, again, you can play with it, but I just want to show you a few things. But this is really cool to play with. So just Google TensorFlow playground. Okay, so this could be solved. This is very simple. Now, if I come to this problem, which is slightly harder, right? Now, these cannot be divided by a single line. I would need at least two different lines to divide this. And so if I run this with a single logistic regression, it'll never it'll never do well because it doesn't have enough complexity in the model. So this is what we call model bias. This model, even if it runs for 1,000,000 years, it'll never solve this problem. And so what I could do is add a hidden layer, right? And if I add, again, the model architecture really depends on base knowledge. The bigger the model, then the more problems it can solve. And now that I've done this, it seems to be able to solve this problem, right? So now the orange is under the orange and the blue is under the blue. And so this particular architecture can solve this model. And again, this is a neural network, right? It has the input layer, the output layer, and 2 hidden layers. Okay. So now this one is a little bit more complex. Let's see what it's going to do. Oh, and that one solves quite well. So the blue is under the blue and the orange is under the orange. And then you can see the model weights. So x1, if I was to write this down, this would be x1 times minus 0.7 into this, times minus 0.3 into this. And then all of these, you'd have to account for all of these going through a sigmoid function. So it gets quite complex mathematically, okay? And then we've got this one. This is the hardest one. And again, what ends up happening is if it can't solve it, if you add layers and you add neurons, the bigger the model is, then it becomes really powerful. And this is where these Gen AI models come in, and that they can encode a lot of information. And so it's learning, and you can see what's doing every iteration. What is it doing? It's making a prediction, calculating an error, updating the weights, making a prediction, calculating an error, updating the weights, until it finds itself not making mistakes anymore. Okay, and so that kind of solves the problem, right? It's doing a loop of orange, and these are orange, and these are blue. Maybe this, if I put an orange here, it would make an error, and then it would clean that up. But at the moment, there is no data there. Okay, and so that's it. That's all I wanted to show you. I hope it makes it clearer. Hello again. So this is ML 103. This is Introduction to Generative AI. This is, I think, the longest lecture here, but it goes into a lot of details on Gen AI. Okay, so what is generative AI? So generative AI, like we said before, is a subset of machine learning algorithms that generates new content. In a lot of predictive ML, the objective, the output of the model is pretty constrained. In supervised learning, if you're classifying that it chooses one of those classes, it doesn't go outside of that. In regression, again, there's a range, it's a number. But so generative AI is able to create content that it hasn't seen, but from information that it has seen before. And it emerged in the public eye in November, I think it was 30 November 2022, when OpenAI launched ChatGPT for free. And before that, Gen AI was really, it is a field that has been around for a while, but in 2022, it was put in the public eye, and the world has never been the same since. And so a lot of what we see, generative AI can create content in different modalities. So it could be in language, it could be text generation in language, it could be image generation, it could be in videos and audios. And so the inputs and outputs can vary widely. But the most success we've had has been in language. A lot of the really cool things are happening in language, and those are fueled by large language models, LLMs. So let me tell you a little bit more about those. So LLMs, as the name suggests, are large language models. And we'll see what large means. And they are sophisticated to observe neural networks, right? We were just playing with neural nets. You should know by now that it's just another formula. It's a mathematical equation that's quite complex. And we played with the TensorFlow playground, which you can build your own neural net. You can decide how many hidden layers it has and how many neurons per layer and how they're connected. I don't think you can change how they're connected. I think it's a feed-forward neural net. But anyway, it's just another type of neural nets with a particular uh, architecture. Large language models are characterized by their large number of parameters. They're often in the billions or trillions. And LLMs understand the probability distribution of words and sequences. If I have time at the end, I'll show you a visualizer of the transformer model, which is the heart of these things. And hopefully you'll be able to see what this means, the probability distribution of words in a sequence. The primary goal of an LLM is to predict the next word. It's kind of greedy in its way of working. It really is a next word predictor based on previous words, and it can capture both the syntax, which is the arrangement of words, and the semantics, which is the meaning of words. And LLMs have proven useful for a lot of things, including translations and natural language generation, speech tagging, information retrieval. There's a lot of different use cases which we're going to look into. And the way they work is they use self-supervised learning for pre-training, which removes the need for explicit labeling. And it's a really cool technique if you want to look under the hood, but this is out of scope for me. Example tasks that LLMs can accomplish, well, we know they can read. Okay, so they have been super useful in things like proofreading, summarizing, analyzing content, classification. We know they can write, so they've been also used as stylistic polishing agents, answering questions, first draft generation, translation, code writing. And because they can read and write, then they can converse. That's actually not necessarily true. It's not because they can do these things. They've been fine-tuned to do that. But we see a lot of chatbots, a lot of natural language layers on top of knowledge bases. And so a lot of common uses, some of the common uses we see is, essay writing, summarization, translation, information retrieval, conversation assistance, image generators, coding tools. There's have been a proliferation of use cases for LLMs. Okay. Oops. Where am I? Okay, so possible issues with LLMs. Well, hallucination is one issue. Hallucination is when a model proper information, and so it comes up with a very reasonably sounding explanation. And because the objective function of an LLM is to optimize for next sequence prediction based on probabilities, it's not optimizing for accuracy, right? It's optimizing for sentences that sound reasonable, not sentences that are necessarily accurate. Okay, so that's a very important thing to know. And so it sounds like human sentences. The actual content and accuracy is beyond the scope of the LLM, right? It has seen information, and if it sees it enough, then the probabilities would reflect that, but it's not optimizing for accuracy in general. Okay, so that's called hallucination, is when it comes up with a response that sounds reasonable, but it's not. It made it up. Knowledge cutoffs. Models only know about data they've seen up to a point. So if a model was trained in 2024 and you say, well, who's the president that was voted in 2025? It does not know because it did not see that information. There's issues with context windows, or that's at least a property, is how much information can it take in or spit out? And that varies widely by models. There's issues with bias on toxicity. The model sees data from the internet, which of course, there's a lot of biases baked into data. And so the model sometimes reflects that. They're still not really great at structured or tabular data, and they're not really good at number processing, and we'll see why. There's a few issues where they're not necessarily great at, but they are very powerful and they do a lot of really cool things, and we'll see some of those things. Okay, so again, I'll go through terminology or glossary. Some of it might seem abstract. We're going to talk a lot about these things in details, but these are things we hear about. So again, we talked about artificial intelligence in one of the lectures. It's techniques that enable computers to mimic human behavior. ML, or machine learning, is a subset of that. So it is techniques that allow computers to learn without explicit programming. So they're mimicking the learning side of humans. Generative AI is a type of AI that allows computers to generate new content. We've seen all of this. Now, what is an LLM? It's a large language model. So it's an umbrella term for models specialized in language. What is a transformer? So the transformer is an algorithm or a neural network that revolutionizes Gen AI and underlies LLM. So it's the heart of the LLM. It's the actual architecture that underlies this LLM. A prompt is the input to the model. It's the actual text that you're giving the model. That's the input. It's called a prompt. A token is a word or part of the word. It's the currency of an LLM. So the context windows that we talked about, how much it takes in or spits out, is it's the unit of measuring input and output size is a token. An embedding is a numerical representation of a non-numerical entity. So it's a projection into mathematical space, and we'll see why this is important. RAG, we hear a lot. This is a retrieval augmented generation. This is the use of an external knowledge base to augment the system. Again, I wanted to put them all here, but we're going to go into more detail. A foundational model is an ML model trained on vast data sets so that it could be applied across a wide range of use cases. So this is a very powerful model that somebody trained that you can use for a wide variety of tasks. So one of the things that people, I think, don't really realize is the size difference between Gen AI models and predictive ML models. And as I said in some of the previous lectures, the bigger the model, the more capable of learning it is. It needs more data, but there's more tunable knobs and more information it can encode. Okay, and so I want to just give you an idea of the generative AI sizes. So MLs, like I said, are sized by the number of parameters. This tells you, this is a proxy for how big the model is. And it ranges from one parameter. So we've been playing with logistic regression, linear regression, sorry, with two parameters, AX plus B. It could be as small as Y equals AX, right? This is a line that passes through the axes. I don't think there's any real use case for that, but you can imagine that that is the smallest possible equation, and they can go all the way to 2 terabytes of parameters. I think if the leaks are correct, I think GPTs are about 1.8, so I'm averaging about 2 trillion. So the predictive ML space is about millions of parameters, right? The biggest ML model that I had ever trained is like, I think, a 64,000 convolutional neural network, right? And so thousands and millions of parameters in the predictive ML space is quite powerful. The generative AI models are in the billions of trillions of parameters. So they're roughly 2 orders of magnitude greater, right? And this is the NLP Moore's law. And so every year model sizes increase by roughly 10x. So we can see that BERT and GPT, for example, BERT is about 340 million parameters here, and this is 2018. The GPT-3 was at 170, and now this is 2021, so it's quite out of date. But now we've reached the 1.82 trillion parameter mark. And I want to give you an estimate of what that means in terms of resources. So a single parameter in a model or a single number, when it's stored in the computer, on the computer, it's stored usually as a 32-bit float, right? And what that takes is about 4 bytes. And so if you've got 1 billion parameters, just as a ballpark, we've got 2 trillion, but let's say you've got 1 billion parameters, that's roughly about 4 gigabytes of RAM just for the parameters to load, right? But when you actually train the model, you need roughly about 20 times more space because of that whole cycle we talked about. So you've got your parameters, you're making predictions, you're calculating errors, you're updating parameters, and you're saving some metadata, and you've got activations, you've got gradients, you've got the optimizer, and so there's a lot of metadata that is saved across that process, and it takes about 20 times more space than the parameter size to train. And so if you've got a 1 billion parameter model, you need about 80 gigabytes of RAM to actually train this thing. And as you see, we were over the 1 billion parameter models a long time ago. These are this of course comes from the Coursera course, Andrew Ng's Coursera course, if you want to look at that reference. So imagine the requirements of about 1.8 trillion model, right? So these systems are very large, and they've put constraints on compute and data, and they've made parallelization and optimization, both at the hardware level and a software level, a must. So there's a lot of work in the Gen AI space to optimize everything from compute to memory to processing to loading, everything. It's really forced us to really push optimizations to be able to better support these things. So this is a really cool slide that I've taken from a lecture that Yann Dubois, a doctoral candidate at Stanford, gave. This is on YouTube. You could see it in the reference section. I have a reference section, and it's if you Google Stanford CS 229 lecture, you should be able to find it. But anyway, these are not my estimates. These are Yann Dubois, but they're really cool to give you an estimate of, again, the resources required for training. And so he uses the example of Llama 3, which is about 400 billion parameters, large. And so it's exactly 405 billion. It's trained on data that's about 15.6 trillion tokens. The token per parameter ratio is about 40 tokens per parameter, which means that it is trained compute optimal. We didn't talk about this, but there is a paper that came out called the Chinchilla paper, which looked at, these are called scaling laws. This is information about how the performance relates, performance and model relates to model size and resources it used in terms of various things we could look at. And in the paper, I think their estimate was that you need 20 times the number of tokens. So there should be 20 times more tokens than parameter size for an optimally trained model, I think. And so this is 40 tokens, so they're higher than that, which means that it's trained compute optimal. And these are the flops. So this is how much in a compute it would need. And so this is the 6NP. So we would need 6 times the size of the data sets times the size of the model, which comes out to this number here. In the paper, they say that they trained it on 16,000 GPUs. That's how many H100 NVIDIA GPUs, which have an average throughput. I fixed the error. I fixed the typo, but I left the O, of 400 teraflops. And so that comes to about 70 days. So if you go in and say, okay, well, this is how much compute I need, and this is how much I have, you divide these two numbers, you get about 70 days. In the paper, they say that you used about 30 million GPU hours, which again comes to pretty close to about 70 days to train this model. And so in terms of cost, Yann Dubois has a lot more information about estimates. He's estimating that the salary of these people is about $500,000 and so on, and more information. But he comes up with an estimate that the price tag of this model training is going to be about 65 to 85 million dollars. And the carbon emitted is about 440, I guess that's tera CO2, which is equivalent to about 2,000 return tickets from JFK to London. Okay, and so this shows you that training a model from scratch, which is really, really intense, and it's not for the average individual anymore. So it's now been constrained to companies that have a lot of resources, and they release these models for general use, either as they can allow you to use it as closed source, as a SaaS solution. So they put an API and they allow you to call that API for cost. Some people like Meta, they release the open weight model. So that means that they release the weights of the models, and so you can play with it and deploy it locally, but they don't release code or information about how it was trained, nor the data set. And then there's open source models, which release everything. So they release the weights, they release the data it was trained on, and the process of which it was trained. So you can reproduce that process. And usually academics go for open source, and so they release everything. They don't have these budgets. I was an academic for a really long time. We don't see these budgets. And so work in academia, interestingly enough, artificial intelligence or machine learning is one of those very few cases where industry has taken over academic, like it has superseded academic research because of small budgets for labs. A lot of what academics do is really focus on algorithms. How do you perfect the algorithm? How do you do smart tricks to be able to do some of these things at a better cost, right? Whereas industry, there's a lot of money, and so they crank up the compute. And so some of the notes is, what is the next model? Well, there's usually a 10x more flops. So the factor of increase from cycle to cycle is roughly 10x. And the complexity of this process, of the training process, grows quadratically with the length of the input sequence. So the more data it sees, then the more it needs a quadratic amount of resources from there. Okay. So again, just to compare predictive ML versus Gen AI, the model sizes are very different. Again, in the millions for predictive ML. For Gen AI, it's the millions of trillions. That means that the data demands are also very different. So you need a lot more data for Gen AI than you do for predictive ML. And of course, that means that the training compute is a lot bigger. And so I was able to train predictive ML on my computer. I don't think most of us can train a Gen AI model, at least not a serious one. Actually, no, I should say Andrej Karpathy, who is who is a really big name in machine learning, has written a nano GPT. Again, you can see this in the reference section. A nano GPT, which is a smaller model. It's less than 300 lines of code, so you'll be able to see what it looks like, and you'd be able to run it and train it, I think. So if you're interested, look at that. And so in terms of training, the way that predictive ML is used is usually you customize the model with your own data. But with Gen AI, the training is usually done by big providers and released to the public. For use cases, predictive ML is better at very specific tasks, whereas Gen AI is capable of general tasks. In terms of cost, predictive ML is cheaper. So cost divides into a lot of things, right? There's the training cost, there's the inference cost, and then there's the total cost of ownership. In terms of training cost, Gen AI definitely costs more. In terms of inference, it should definitely cost more because it's a bigger model. But it depends on whether you're using a SaaS solution or you're deploying it yourself. But in general, predictive ML is cheaper. Where it becomes cheaper to use Gen AI is if instead of training, if there's not a predictive ML model that's pre-trained, and you have to hire people to train that model and find data and do all of that, and a Gen AI model can already do that, you really save that piece. And so when a pre-trained predictive ML model doesn't exist, then a Gen AI model can be cheaper because you're saving on setting up that model, if you will. So the difficulty in predictive ML, like I said, is really understanding data and data processing, ML algorithm, ML ops. It's a pretty complex process. The difficulty in Gen AI is really about model selection, prompt engineering, evaluation, because they produce open-ended results. In terms of AWS tools, predictive ML, the main service for that is Amazon SageMaker, and for Gen AI is Bedrock. Okay. So now choosing Gen AI versus predictive ML. The main difference between Gen AI and predictive ML, there's a lot of differences, but the main three big ones is really the model training. Usually for Gen AI, you can't train the model from scratch just because of the estimates that we just saw. In predictive ML, it's a lot more, it's easier, and so a lot of people do it. In terms of, and often there is a lot of pre-trained models out there, but sometimes for your particular use case, you might have to train your own model. The model sizes and the required resources are just vastly different, like we just saw. And GenAI produces open-ended outputs, which makes them a lot harder to evaluate. What I recommend to people is use GenAI foundational models for general tasks, for quick turnaround. So if you want, you don't have the time to get your data, to train the model, to evaluate it, to deploy it, to run that whole cycle, then a foundational model that is ready to go is a good option. If you don't have the expertise, then something that is pre-done is better. But if you can find a predictive model that's pre-trained, it's going to be cheaper, and I'll show you an example. And if you don't have data, then foundation models are a good idea. You use predictive ML for very specific tasks, tasks that require great accuracy, because you can control accuracy and compliance a lot more with predictive ML than GenAI. If something is a long-term project, the price of a GenAI model will catch up to you. If it's a really long-term project, training your own model in the long run will become worth it. And if the project load is really large, so if you're pinging that model millions of times a day, then again, the costs will catch up to you. And so owning your own model and having a smaller model that's customized for you is definitely a better idea. And if you have high compliance projects, because you have a lot more control potentially over a predictive model than a GenAI model. Okay, so I'm going to give you an idea about the trading data. Again, I'm going to go through it fairly fast, but it's good to see. Collecting data is really hard work, and often it's a heavily guarded secret by companies. They don't always tell you what they're doing and how they're doing it for a variety of reasons. I mean, some of it is because they think of it as the secret sauce from what the model is learning. A lot of it also is because there's compliance and legal issues and patent laws, and it's not really clear what is being collected and how it's being used, which is very unfortunate. But anyway, we don't always have that information. But here's an example of how this process would go about. You would download all of the internet. And so people use web crawlers. You can look at Common Crawl, which indexes the internet. There's currently about 250 billion pages online, which is roughly about 1 petabyte of data. And you extract the text from the HTML. So when you scrape the internet, it's all HTML docs. Of course, you extract the actual text from it. You filter undesired content. You do deduplicate, because of course a lot of pages are found in different places and several times. You add heuristics to remove low quality documents. There's some model-based filtering as well, again, to filter out some stuff. And then you classify your documents to be able to decide on how much to use of what, right? You definitely don't want a model that's trained on social media predominantly, right? So understanding what the documents are and what they relate to and so on is important. And then you use that to train your model. Again, this is the devil's in the details, and this is a really high overview. I think probably the data part of ML is usually the longest part of ML. And so this just gives you an idea of the steps, but this is a long and painful process. There's some open source academic data sets if you're interested. There's the C4, the Pile, Dolma, and FineWeb. And if you Google those, you should be able to find them online. And so again, like the bigger the parameter the model is, the more parameters it has, then the more data it needs to see. And today's models are trained on about 15 trillion tokens. So we saw in the Llama 3 model, it was about, I hear 15.6 trillion around. So that's where models are today. In the words of Jan LeCun, it's trained on enough data that it would take you and me 20,000 years to read. So these things chug a lot of data, and they have a lot to learn from. And honestly, the way they work, they can do some wonderful, some really amazing things. But again, they're really big models, and they see a lot of data that you and I can never process in our lifetime. Okay, how to choose an LLM. So one easy way to choose, of course, to constrain your options is looking at the input and output modalities. So different models, there's some models that take input text and output text. There's some models that take text to image, image to text, videos, and so on. And so you need to understand what is going in the model and what is coming out, and that already reduces your pool of models. You want to look at the performance on required tasks. So LLMs have a lot of different capabilities. And so there's a lot of evaluation metrics out there that they're run on. And so there's data sets, evaluation data sets that look at reasoning, some that look at coding, some that look at summarization, and so on. And so if you are interested in a coding model, for example, you would want to go and pick a model that does really well on coding evaluation tasks. And the way you do that is you look at the model card. The model card is, you can think of it as the ID of that model. It's the ID card of that model to tell you what that model does, what's the input, what's the output, how it was trained, how big is it, what is it good at, and so on. And so by looking at the model cards, you would be able to potentially choose one. Just as a ballpark for model sizes, a model that is roughly 1 billion parameters is good with pattern matching and basic knowledge of the world. When it gets to the 10 billion, it has greater world knowledge and it can follow instructions, basic instructions. But when the model gets over 100 billion, then it has rich world knowledge and complex reasoning. So depending on the task you want to do. But again, I think very few, no, we have 70 billion llama models. So you can, depending on what you do, the bigger the model. It's true that the bigger the model, the more tasks it can do, but it also means that the more expensive it is to have and maintain. Then there's the closed source SaaS option versus the open source model options. So SaaS models, again, are easy to use in application because they're calling an API. They're more powerful models because these companies have a lot more money than we do. Not true, actually, with DeepSeek now. But again, closed source is more likely to, because of the money involved. I am a great proponent of open source because with collective knowledge, we can get further. But again, the cost of training is not trivial. In terms of open source, again, you've got full control over the model. You can run it on your own devices. You can have full control of the data privacy, so you're not sending your data outside of your domain. There's a lot of other things you can consider, but these are some of the things that I look at. There is a difference between the predictive ML and the Gen AI lifecycle. So in terms of the predictive ML lifecycle, what we do, again, we looked at this, we frame the problem, we source the data, we choose the model, we train it, we test it, we deploy it, and we maintain it. And we looked at this a couple of times now. In terms of the Gen AI lifecycle, what you do is you scope your project, you look at your business requirements, then you build the system. So you choose the model, you prompt engineer, you adapt that model to your needs, then you evaluate your performance when you're happy with it, you deploy it, and you monitor it. The main difference really is about this whole sourcing your own data and training, which is not present in Gen AI. Again, because of the price tag, maybe one day. So whereas predictive ML, much of the work is about customizing the model to excel at a specific task, Gen AI is more about extracting what you need from a general purpose model. So this model knows a lot of things. It knows 20,000 years worth of data, 15 terabytes, trillion tokens, 15 trillion tokens. And you're asking it for maybe what, 100 tokens or 1,000 tokens. So it's really like asking for a needle in a haystack. And so how you frame that question or how you talk to the model would kind of helps your success in getting what you want. And so this is where prompt engineering comes in. Prompts are, again, like we said, the input to that model is your question, is what you are telling the model. So prompt engineering is editing that input or playing with it to drive the desired output from the model. And if we want to think of the prompt, again, this is the input to the model. There's a question there. The most important thing, the required thing is the query, is what is it that you want this model to do, is the question. But then there's a lot of other things that you can add to the context of that prompt. And so you can give it instructions of how to perform the task. You can give it an objective or a mission to achieve. So you can tell it, we are trying to accomplish X. You can give it a persona. You say, okay, well, you are a doctor or you are a lawyer. This changes the lens with which the model gives you the response. You can give it constraints. So you'd say, oh, avoid this or don't do that. You can give it examples of the output. So you demo the output. This is where 0 shot, 1 shot, or few shot learning comes in. So you give it an example and it allows to, it tries to mimic it. Context, so more information. Now you give it tone. You can give it, there's a lot more that you can do. But what I want you to know is that, again, this model is huge. It's seen a lot of information. You're trying to get at a very specific response out of it. And so the more well-formed your prompt is, that the higher your chances of success. And so prompt engineering best practices: give clear instructions, structure your prompts, include examples. So use all of this that is available for you, right? Use instructions, chain of thought really helps. That's when you tell the model to explain how it's done something. Break down complex tasks, prompt iterations, so you keep trying until it works. Okay, where are we at? 34 minutes. Okay, enhancing LLM performance. There's several ways to enhance LLM performance. I've divided them in two main categories. There's weight preserving techniques. This means that the model itself is unchanged. The model weights are the same, but what you do is you focus on how you interact with that model. So an example is prompt engineering. You are changing what input you're giving it, but the model itself is not changed, but that does increase performance. RAG, for example, when you add an external knowledge base as well, that helps the performance of the LLM without changing the LLM itself. There are weight altering techniques, so the model itself changes. And so you're fine-tuning, you're pre-tuning. No, you're not pre-training. This is from scratch. This is too expensive, but you're fine-tuning so that you add a layer. And there are a lot of different techniques like PEFT, parameter efficient fine-tuning, and other ways that have been, and quantization and so on, that have been made to make handling models a lot better. Okay, so there's the weight altering techniques and the weight preserving techniques. The way you should go about it is try the weight preserving techniques first. So do your prompt engineering, then your RAG. If that doesn't work, then you move on. Don't start too complex because it's going to get expensive very fast. Okay, so what is retrieval augmented generation, or RAG? This is a method created by the FAIR team at Meta to enhance the accuracy of an LLM. It improves LLMs by adding the information, by an information retrieval step before generating an answer. And so what we see here is you've got your user, they've got a prompt, this is the question, and you've got an external knowledge base here, and it could be anything. It could be the documents from your company, it could be field-specific information. And information is retrieved from this database. It's used to augment the prompt and then sent to the model, and that kind of helps the model in different ways, and then you get a response. Okay, so this is the simplest. This is a basic vanilla RAG architecture. It's pretty simple. And so the benefits of RAG is it allows you to potentially cite resources because you've got all of this metadata here. Data and metadata. You can add up-to-date information beyond the cutoff date of the model itself. You can add domain-specific knowledge of your field. You can add specific knowledge to your company, perhaps. It reduces hallucination because it gives the model more resources, and it improves performance without actually training. The trade-offs, of course, is that it does increase latency. You've added an extra piece of the system, and it increases cost. So you've added this extra system, right? It's cheaper than actually changing the model, but it's not cheaper than just using the prompt engineering, for example. This is a more complex view of this. So when you want to set up a RAG system, there's a few steps you can go through. So these are documents, you can chunk them. You chunk them, which means you cut them into smaller pieces, or you divide them into smaller pieces. And then you embed them, which means you vectorize them. We'll talk a little bit about what embedding and vectorization is in a little bit. But you go through these steps, you chunk, you embed, and then you store it in the database. And then when you want to use the RAG, you query the database, you retrieve the information you want, you add it to the prompt, and then you generate the answers, okay? Now, there's again, this is an abstract representation of this. The devil is in the details. There are so many decisions to be taken at every step of these. How do you chunk? What metadata do you save? How do you embed? Which embedding model? How are you going to retrieve? Are you going to retrieve based on semantic search, or what function are you looking at similarity at? There's so many details across of this, but my point in putting this series is to really give you an abstract view so that it's not as intimidating as it seems. Okay, Gen AI under the hood, concepts that are important in LLM. So the tokenization. Tokenization is the initial phase of interacting with LLMs. What it involves is the breakdown of input text into smaller pieces known as tokens. And we'll talk a little bit more in detail about this. So tokenization is model dependent. Each model ships with its own pre-trained tokenizer and model weights. And embeddings involve transposing the words into mathematical space, and we'll talk a little bit more about this. And the transformer is the model at the heart of the LLM. Again, we're going to have slides to talk more deeply about these. So what is tokenization? Again, it's the process of breaking down the text into smaller units called tokens. The benefits of this is cost efficiency. So the transformer performance, like we said in the last structure, grows quadratically with the terms of the input token. So if we were to tokenize, if we could break words down into letters, that would make the input a lot longer, and so the performance would be terrible. It would be really expensive. Tokenization reduces the space complexity of words. So when you tokenize, then the space is a lot less. So instead of having all of the conjugation of the words, for example, you would have the base word and then the possible conjugation. So instead of, which reduces the space complexity, you would have less information there. It's really good with things. It's useful because then mistakes, spelling errors, and things like that are not as dramatic to the model. The side effects, of course, is that it creates a lot of weird behavior in the model. So LLMs cannot spell words because they don't see letters like we do. They see tokens, and so it doesn't understand the letter layer. They cannot do simple processing, string processing, again, because they don't see letters, they see tokens. They are worse at non-English languages because it's not the same. The tokenization is optimized on the English language, and so other languages might not work as well. It's very bad at simple arithmetic because instead of the tokenizer cuts numbers at different rates, it doesn't see it as the base 10 system that we do. And then it has trouble coding in Python, again, because of the tokenization of all of the spacing, which some of these have been fixed in various models, but some of the reasons for these is really tokenizations. And different, again, like I said, different tokenizers, different models come with different tokenizers, and this website can show you what the tokens look like for different models, and so you can play with that. This is an example of hello there, it's nice to meet you for the tokenizer for Google, Gemma, and GPT-4o, and you can see here that the apostrophe S is treated differently. This is such a small sentence, but you can see that there is a difference. Okay, word embedding or vectorization. So machine learning models are just large statistical calculators. They work with numbers, not with words, right? We as humans communicate with words, but models and math works with numbers. And so we have to convert the words into numbers. And this is what's called embedding or vectorization. So vector embedding, vectorization, embedding are all the same things. It's really a projection of text or images or whatever your input data is into mathematical space, which means numbers. And so again, this is a numerical representation of non-numeric entities. And there's different examples of how we did this across ages. And so one-hot encoding, for example, if you have an example, that's one way to vectorize a discrete class. TF-IDF, which is term frequency inverse document frequency, was one way we did it before. Word2Vec is really cool. Here's the paper. So historically, some examples are in the 1954, there was what they called bag of words, which is a simple approach. What it means is they just counted words in a document. So the more if there was more sports words than anything else, then they would categorize it. This was mainly used for classification. They would classify it as a sports document, for example. But that was the simplest way, is how do you take words and get numbers out of them? And counting in the 1954 was the easiest way. And so this was where bag of words come in. In 1972, it became a little bit more sophisticated, where TF-IDF means the term frequency inverse document frequency. So you counted, but then you divided by how often that term appears in the document. So it's a frequency count. Now it's not a base count or an absolute count. It's a frequency. And then in 2013, Google released the Word2Vec, which was really, really cool, and I think is underlying a lot of the advancement in NLP that we see today. What this is high dimensional vectors encapsulating semantic associations. And again, this I think is one of the flag moments. This is a pivotal moment, advancement in NLP. And what it really showed is, so what they did is they took this model, embedding model, they gave it a lot of text data, and they trained it, and it came up with these vector embeddings, vector representations in high dimensional space. But then what they showed is that you can do math with words. And so if you said something like king minus man plus woman, the model would give you queen. And so this transformed NLP and modeling on text, because now we understand that we can do that projection really well. And that's the paper, and you can read a little bit more about it. The transformer, this is the last big component I wanted to talk about. The transformer is really the architecture that the model architecture that is at the heart of the LLM. It's the heart of many LLMs. It's a neural network. Again, we played with neural networks, so if you're not familiar, go back to the previous lectures. And it was introduced in a paper, which was called Attention is All You Need in 2017. This was work from researchers from Google and the University of Toronto. It was initially designed for sequence-to-sequence tasks, like translation. I don't know that they knew that it would take the world by storm. This is what it looks like. So again, because these things, the mathematical model tends to be too complex, we visualize them abstractly like this. So this is, you got your inputs. I don't want to go into too much detail, but you've got an encoder, and then you've got a decoder, and then there's a cross attention in between. There's a really good lecture on YouTube, again in the reference, about how this all works, and you can build it from scratch if you want. So look at the references. But what a lot of people in the field did, this started as a translation paper, and then what in 2017, and then what people did after that is they copy pasted the architecture and changed the input. So they changed the embedding, the vectorization, the embedding, and it does wonders. I mean, it's still at the heart of a lot of things we do. There has been some changes to the architecture, very minor, from the paper, but again, you can take a look. The main, before that, the way we did sequences was through RNNs, recurrent neural networks, and their different variations. But those dealt with data sequentially, which meant you couldn't parallelize them. And so RNNs, you could look into them, but the differences that made the transformer the next leap is because it was parallelizable. And so we can train this on distributed compute, and it can get a lot larger. They introduced something called positional encodings, where it doesn't need to retain the sequence anymore. It retains a vector of where every word is, and that helps it not retain sequence, and it helps again in parallelization. And they introduced something called attention heads, which allows the model to assign different weights to different words depending on their context. There is this I wanted to show you. I think this is my last slide. Yeah, okay, so I wanted to show you this. This is a really cool website. Again, you can see it. This is based on the Nano GPT. And what this shows you is, this is the embedding, this is the input. Okay, so you've got your data, this is the words, and this is the embedding vector, right? So you've got your tokens. There's tokenization, and Data visualization empowers users. So you can see here that empowers has been split into two different tokens. So already this is tokenized, you can see. And this is the positional encoding. So this is the position of each word. And then it's been vectorized. So this is the embedding, the vectorized. So this word has been changed into this vector. And this is using a vector representation that is 768 numbers long. The vectorization changes from company to company and from provider to provider. Google uses a vector that's 768 in length. I think GPTs are closer to the 3,000 mark. The more numbers you have in that vector, then the more dimensionality you are gathering. And so there's more information that you can potentially collect. So just keep that in mind. So this is 768. It's late here. And so now what you see here is this is the information, and it goes through the, the layers. This is distributed, so these are different processes happening. And then you can see here there's attention, so it's giving different words, different evaluations or importance, and it goes through the layers. And what ends up happening, what I want to show you is right here. It takes the tokens and then it creates a probability distribution. So this is the probability distribution. And so it says data visualization empowers the users to make, and it's a next, remember, it's a next word predictor in the sequence. And so this is the possible words that could be next. And it thinks that the next word based on the probability, 28.3, is visualize. So data visualization empowers users to make visualize. Now, again, this is not a great model, and that is the Nano GPT. It's a small model. It's not been trained on a lot of data, but it gives you an example of this, how this whole thing works. Now, temperature, I didn't talk about temperature and top key and top K. These are hyperparameters that you can, or just variables that you can change that change the model behavior. And what these do is they change the randomness in the model. And so if the temperature is 0, what you can see here it's doing is it's changing the probability distribution at the output layer. And so if this is 0, this model becomes deterministic. It gives the highest, the top word, the highest amount. And so it'll repeatedly do that if you ask it over and over. If you make this highest, then you can see it changes the distribution. There's a lot more randomness. Now the probabilities are very close to each other, and so it will choose one at random different times. So these are what the top P, top K, temperature, they really play at the level of the probabilities. Okay, so that is it for me. These are my references. Yann Dubois' lecture is really good. It goes into what LLMs are, and it is more technical. It is a Stanford lecture in CS, so it goes a little bit more into the weeds if that's what you want, but I personally enjoyed it. There's some lectures here from Andre on, he does a lot about how do you build a GPT, how do you build a tokenizer, how do you do all of these things. Really cool if you're interested in the depth. I personally really like Andrew Ng, and I follow him, and I take a lot of his Coursera courses in Deep AI. So these are there for you. And that is it. Hello again. So this is the final lecture in this mini series. So this is ML 104, Architecting Gen AI Systems. And so this is a reminder that the tech and ML serve the business, right? So it has to be linked to the use case. It has to be the proper tool for the use case. So the first question to ask is AI/ML the right tool for the job? And whether it's ML, AI, analytics, tech, they're all tools to solve problems. But you have to choose the right tool. ML and AI are pretty powerful, but well, if you have a hammer, I guess everything looks like a nail, but ideally you would choose the finest tool for your job. So any repeating task in a system is worth automating. If that task is deterministic, you know the rule, you know the system formula like we just saw in the previous lecture, then you can automate that with with a software system, with DevOps, with rule-based systems. If, however, the task involves cognition or reasoning or a pattern you don't understand, then that's where ML comes in. And again, anytime you have data, then ML is an option, like I said in the previous lecture, but it really shines when there is change, when there's scale, and when there's complexity. Okay, but again, you just have to look at what your use case is, what are your possible options, and if ML is your best option. Now that you've chosen AI or ML, you have to choose whether it is predictive ML or Gen AI, and we went a little bit over last lecture about when to choose either. This is a reiteration, but here what I want to show is that both in predictive ML and Gen AI, you can have custom models that are trained on your own data or a SaaS solution. So this is a pre-trained model. And it could be a pre-trained model that you deploy yourself, or it could be a pre-trained model that is hosted by a provider for you. Either case, I didn't put an extra line here for that, but like we saw in the last lecture, custom models in the Gen AI space are very, very costly, so that's unlikely to happen. And predictive ML solutions in general, there are pre-trained models out there, but the majority of cases are usually custom built. And so we said this before, but the main differences to keep in mind is that the model size is very, very different. The training, there is a lot more work in training and data gathering and so on, predictive ML than in Gen AI, and that Gen AI gives open-ended results, right? And so the predictive, the cases that we see normally, so again, this matrix, you can have predictive ML that is custom, or that ones that are pre-trained, or the ones that are provided by a third entity. And in Gen AI, you can have all three as well. But the pattern that we see most in the wild is that Gen AI, people use a third-party option, an API call. And in the predictive ML space, it's usually custom models. So when I'm talking, I'm going to compare these two. Again, I understand it's not apples to apples. But these are the patterns that we see more often. And again, when I say cost, there's it's a proxy. There is training cost, there is inference cost, and there's total cost of ownership. And of course, there's the cost of having personnel and training personnel and collecting data and so on. But on average, Gen AI tends to be more expensive. And so this is again, we've seen some elements of this. The model size is a lot bigger. The initial training investment is a lot bigger in predictive ML. I think this should be clear by now. You have to collect your data, you have to train, you have to have the skill set. So the data availability is required here, whereas it's not in Gen AI. The expertise is required, whereas it's not in Gen AI. Not as much anyway. So the initial investment required for predictive ML is a lot higher than it is for Gen AI. So if you have a use case where you really want to hit the ground running and prove value really fast, then Gen AI might be a better option for you. In terms of inference cost, again, it's not apples to apples, but on average, Gen AI tends to be more expensive because these models are bigger, because they're more expensive to host, because that model provider needs to get their service paid for. In terms of model control, you have a lot more model over a custom, a model that is custom to you, that is yours, as opposed to a model that is hosted by somebody else. In terms of deterministic or not, predictive models are a lot more deterministic. Foundational models or LLMs tend to be a lot more probabilistic and less deterministic. And so depending on if you have and I said this before in the lecture, so this is a repeat, if you have a project that is really long-term, it's a long project, that it makes sense to use predictive ML because the cost of Gen AI is going to catch up with you. Again, if your workload size is really large, again, the cost will catch up with you. So a predictive model might be a better option. And if you have high compliance, then a predictive ML, custom predictive ML model is probably a better choice. You control a lot more than you do with a foundational model. So now this is here we're comparing apples to apples, and that here we're looking at a predictive ML SaaS solution versus a Gen AI SaaS solution. So this is document processing. Textract is an AWS service that is a model as a service. It's a pre-trained model. And I'm looking at what it would cost to process about 1 million pages a month with the assumption that there's about 676 words per page. And if I do that on Textract, that gives me about 1,500 USD a month. If I do that on Nova, Bedrock through Nova, it'll cost me about 2,600, which is a 2x roughly. If I do it on Cloud Sonnet, it'll cost me 11,000, right? And so Novas are, they're surprisingly cheap. I think that's one of their good features, is that they're fairly cheap. But the idea is that if you have a predictive ML model that is pre-trained and does a specific task that you want it to do, that model, again, different environments and different things might vary, but I am willing to make the bet that it'll be cheaper than a Gen AI model simply because of the size and the resources required to host a model. Okay, so we're going to talk a little bit about, so let's say you've decided that ML is a great fit for their use case, and within AI ML, you've decided that Gen AI is a better fit for your use case. So let's say you need to show your stakeholders really fast value, and so you don't have really a lot of time to think about custom models. There isn't a SaaS, there isn't a pre-trained model that does exactly what you want it to do, but an LLM does it for you. So that's you've decided that hypothetically that Gen AI is the thing for you. Let's architect a system. And so what I'm going to show you here is a series of conceptual diagrams. So they abstract the main building blocks in a system and how they are connected. There are many different tools that can fit into these blocks. So when I say a RAG system, there's many different ways. There's a million ways to roam. There's a million ways to build that system in technical terms, but it serves the same function. And so I'm trying to help you abstract all of the important building blocks. And so the main point of this exercise is really to get a high-level view of the system. And it's very important to understand what the function of that service is, or that piece, that component, what the pros and cons of having it are. And then once you get that and you decide that that component is important to the system, you can go in and dig into the technical implementations, what tools fit into that or serve that function, and how you would implement that. That is beyond the scope of this particular call. I'm just looking at conceptual big component diagrams, but I think within, if you're taking the Gen AI free bootcamp, then you're going to have some opportunities to do that work. Okay. So Gen AI architecture ground zero is a model call. By the way, these series are not exactly, but they are based on the book AI Engineering by Chip Huyen. I really enjoyed that book. I like both her books, actually, so it's a really good resource. The first book, which is Designing Machine Learning Systems, that talks more about predictive ML, and this one, Gen AI Engineering, talks about generative AI. Okay, so at the heart of a Gen AI system is a Gen AI model. We're going to call it a generation model, and so let's say we're using text here, so it's going to LLM. And the way the system works is you've got the model here. The user sends in a query. Again, we call this a prompt, and then gets a response, which in the field is called a completion. Okay, gets a response, which is a completion. And already, this is a very, very powerful system in that these models can do a lot of things. So they can summarize text, they can classify text, they can answer questions, they can write drafts for you, they can write code for you. There's a lot of things that these things can do. They're pretty impressive, actually. It is important to note that if you are using a a foundational model by a third-party provider, you're not hosting it yourself, that this here, I should have put a line here, this is within the domain of the model provider. So the data is going outside of your own jurisdiction. Okay, so this is at the heart of the system. This is the biggest piece, is the model call. Now, like I said in previous lectures, these models are very big. They have a lot of encoded information, and what you're looking for is a particular answer or some sort of query that you're looking at or information. And really, it's like looking at for a needle in a haystack. And so what you want to do is you want to give that model more information and more context for it to be able to help you the best way. And so that's where the anatomy of a prompt comes in. So I'm not going to go through this in detail because we already did in previous lecture. If you've missed it, please go back. But the idea is that a prompt, of course, is the input. Like I said, prompt engineering is the process of editing the input or formulating the input or formatting it to drive the desired output. And the prompt itself, as at the heart of it, is a question, a query, what it is that you want the task, what task do you want the model to do? But that's not all of it. You can add so many things to a prompt, and so you can add instructions. This is steps to perform. You can add objectives, so you can tell it something you want to achieve, the goal you want to achieve. You can give it a persona, so you tell it, oh, this in terms of context, you are a doctor, you are a lawyer, and that gives you different viewpoints. You can give it constraints. You can say avoid this or don't do that. You can give it examples, so you can give it a demo of the output. So this is where a 0-shot, 1-shot, and few-shot learning come in. Or you can give it more context for relevant information, or you can change the tone. And there's more. This is just an example, but the idea is that you can change the prompt, you can enrich the prompt for the model to be able to help you better. So you can give it more instructions. And so this is what we've added here. We've added this system where you are adding the context construction. So this prompt here that we're building, you're building it a little with a little bit more awareness, right? And so that comes here. So as I move through these diagrams, the new piece that I'm building in is in orange and the rest is in black, just to allow you to follow through. So we enhance the context or the prompt or the model input. And so this becomes a little bit more information for the model, right? The other thing we can do is to add an external knowledge base. This is a RAG system, so you've got a database here, and then the input retrieved from that database goes into the prompt construction, and then it's given to the model. There's a lot of reasons why you would want to add RAG. Again, we talked about RAG in the last lecture, so you can go back and see that. Now, if you want, you can add guardrails for your model. So as again, like I said in the beginning, if you are using a SaaS solution from a model provider, then again, this piece right here, or this here, this generation call, that is not in your domain. That goes to the provider. And so there's information here crossing your company network. And so what you can do here is you can put input guardrails. What that does is it validates that the input going out of your organization is based on your norms. It's compliant with your norms. Is there any PII in there? Do I mask anything? Is any information, sensitive information that I don't want out of my company? And so that's where input guardrails come in before they leave your network. And then you can add output guardrails because because LLMs give open-ended outputs. You can put output guardrails to check whether again the response is compliant with your requirements. Is there any safety constraints? Is there any bias? Is there any profanities? All of that stuff that you wouldn't want your user to get, you can put a catch right here. And so now we've augmented the system again with these guardrails. What we could also do, for example, is add routers and gateways. And so what this does is that this model generation this generation piece here is a model. It goes out to, this is a model call. And what happens is that different models have different strengths. So some models are better at reasoning, some models are better at coding, some models are better at summarizing, and so on. And if you have users that, if you're supporting all sorts of requests, you might want to do different model calls based on the user input. And so what you would do is you write this class, a wrapper class, which is, we're calling here a model gateway, which routes different calls to different models depending on certain criteria, right? What this does is it abstracts the model use from the underlying model. It just puts an abstraction layer, which allows you to switch models seamlessly. Okay, now, again, one added, something else we can add as well is caches. Caches in different parts of your system can reduce latency, but they also can reduce cost because you're not hitting your databases or you're not hitting that model as often. Oops, and so you can add caches at the query level, you can add them at the knowledge base level, and you can add them in different places. And again, there's all sorts of questions about what types of caches and how do we cache and when do we, that in all of these different scenarios, there's all sorts of detailed questions that can follow, but I'm just showing you an abstract system. And so you can also add functionality with agents. So you can add agents that do various things. And then you can add all sorts of interesting, it is a software system at the end of the day, right? You would want to follow best practices. You add authentication, authorization, state and session management, monitoring and observability, pipeline orchestration, human feedback. There's so many other things that you can add to make this this system production ready. But what I wanted to show you is, had I shown you this, I hope this is now understandable or seemingly digestible, but had I shown you this from the very beginning, it could have potentially looked intimidating. What I want to encourage you is to really look at everything you look at online, all the different diagrams from this lens, from the conceptual lens, and try to understand what the component is, which bucket does it fit into, what does it do, and then not to really get bogged down with the technology. The technology changes really fast, and it's moving super fast, but what you really need to have is an overview of the system and the components. Okay, and that is it. I hope the series was useful. If you have any questions, let me know. I am going to release the slides with the Jupyter notebooks. I think that's it. Yeah, the slides in the Jupyter notebooks. Hope this was useful.